Here is my interpretation of this confidence interval. There is a 95% probability that the mean number of days lost to illness in this company is between 6.28 and 7.72 days. There we go. So you might think that compared to the last problem I did, this confidence interval is a lot more tightly focused. Well, that was due to not only the larger sample size, but also the smaller standard deviation. Well, okay, so 95% probability that the mean number of days lost to illness in this company is between 6.28 and 7.72 days. There that is, which means what? There's a 5% probability that I'm wrong. Okay, on one side there's 2.5% probability that it's more than 7.72 days average for the company, and 2.5% chance that it's less than 6.28 days for the company. So in statistics, always a chance for error when you do estimation or hypothesis testing, and we accept that there's a chance that we're wrong, but we can control that amount of error by how we do these things. So now I want to compare this to a Chapter 7 problem, and I think this will help clarify why are we so interested in this estimation. So I need to find the problem in Chapter 7. Let's see, it's sorry about that. Here it is. It's on page 308, number 47. So let's read along on page 308, this problem. The mean number of days of work or school lost by a person to illness is 5.1 per year, according to the National Center for Health Statistics. In a small business firm with 49 employees, the mean number of days lost to illness was 7.0, with a standard deviation of 2.5 days. The firm owner wonders if the employees are sick more often than should be expected. So in Chapter 7, what they're asking you to do is to compare the company's mean number of sick days with the national average of 5.1. You say, well, obviously these employees miss more work. They average 7.0 and the national average is 5.1. Well, yeah, that's a pretty fair gap, but in statistics, we don't know exactly where the dividing line is between something that's so close it doesn't matter and something far enough apart that it is significantly different. For example, okay, again, our sample mean showed 7.0. Suppose that the national average for number of days work lost per year was 6.8. So 7.0, 6.8, very close together. You think, well, our company could be the same as the national average. It's close enough. It's within tolerance, because there is some random variability. 7, what's the difference between 7 and 6.8? There's not much difference. We would say, oh, there's no difference. Okay. However, what about 5.1? Well, maybe that's far enough to say, ooh, that's significant. That's a big difference. And in fact, look at our confidence interval. The national average is 5.1. It's below the confidence interval. Okay, so if this is all valid, as far as these numbers for this company, and the national average is 5.1, then because 5.1 falls outside the confidence interval, we have a very good reason to say, well, this company, these employees are sick more often than the national average. It is statistically significant. And because it falls outside the the estimation of the population mean for the company. All right, so ponder that. That's one use for confidence intervals. Now, I should level with you in my reading, looking through various medical and psychology and sociology journals in our library, where you see a lot of, professionally done statistics. There are confidence intervals. They're not very abundant, but they are in there. So people do confidence intervals for various reasons in publications. And not as common as what you will see done in Chapter 7 or even Chapter 10. And but they're there. Okay, well, I'm going to erase the board, and before I do a couple more calculations, I wanted to show you a neat handout that I have.